All right. Thanks so much once again. And thank you for inviting me again to speak at the Data Science Conference. It is with great sadness that I could not actually come to Serbia for the event, but I still hope that the exposition presented here virtually will be of interest to many of you. What I'm going to be talking to you about today, I'm going to be talking to you about one of, in my opinion, the most exciting developments that are taking place in artificial intelligence right now. And specifically, it's one that's not only very close to my heart, but one that also I've had the great honor and pleasure to contribute to in previous years. Specifically, I'm going to be talking to you about the amazing potential of combining top-tier artificial intelligence systems in synergy with human domain experts and the transformative potential that can have. So let's try to talk through what I mean by this, and we will deliberately be taking it a little bit slower because of the diversity of the attendees in audience today. So because this is a data science-oriented event, I probably don't need to spend too much time talking about many of the amazing things artificial intelligence can already do today, or the many ways in which it already interfaces with our day-to-day lives. But one thing that I think is very important to note, and just so I want to make sure we're all on the same page as to some of the interventions we're going to be doing with artificial intelligence systems during this talk, I'm going to start actually by making it very clear what we mean by modern day artificial intelligence. So as probably many of you know, what we mean when we refer to artificial intelligence in today's day and age is actually this red dot of deep learning methods, which broadly speaking focus on techniques that are capable of learning meaningful representations directly from raw data. And the key insight that deep learning rests on is that if you want to build a smart machine, it's much harder to program it to be smart than to program it to learn to be smart by itself. What do I mean by this? Let me start with a simple exercise. And I used to do this interactively with the audience, but obviously in this case, you have to imagine it for yourself. I'll start by asking you, what do you see in this photo? I promise you, this is not a trick question. As you probably immediately jumped to this conclusion, what you're looking at is a cat, right? However, if we want to program a smart system that is able to look at this particular picture of a cat and tell us, indeed, this collection of pixels is a cat, we need to give it some rules. So I want you to think about not just what you see in this photo, your brain immediately probably figured that out, but also why did you do that? Like, what did you see in this collection of pixels that made your brain think you're looking at a cat? And after a bit of time thinking, you probably might say, yes, it's the eyes, it's the ears, the fur, very characteristic properties of cats. So you may then be tempted to write a program that tries to hunt for characteristic big eyes or ears and then classifies a cat based on those things. Well, I take your proposed features and I raise you these two counter cats that you can see in the upper right of the slide, right? These two cats obviously do not feature large eyes or visible large ears. And in fact, the second cat is even completely blending with its environment. So it's really hard to tell where the environment stops and the cat begins. Yet still, I bet you looked at these two cats and your brain was still immediately able to figure out that what we're looking at here is a cat. And, these were all cats of a fairly simple color and shape. I'm not even starting to talk about the huge variety in colors and sizes that cats can have. So it seems that trying to write a collection of rules that will look at an image and tell you what you're looking at might be a bit like Mission Impossible. But then what we in deep learning try to do, right, is we try to look back to the human brain. Like, how is it exactly that you have been able, even though there's such big diversity, how have you been able to figure out that all of these things are cats? Well, in reality, the advantage you have over this computer is that you've seen many, many cats during your lifetime. And at a few occasions, you probably had someone behind you, some kind of supervisor, like a parent or otherwise, that told you that what you're looking at is a cat. And then your brain managed to connect this collection of observations to the concept of a cat. And that's exactly what we kind of try to emulate with deep learning. We try to build these systems, these neural networks, which have a bunch of parameters. and they take these pixels of the image and they spit out an answer on what is on the image, for example, cat in this case. Well, in reality, initially it will be completely wrong. With the basic initial parameters, it will say this is an elephant or something like that. But over time, with feedback on how it's wrong and in what ways it's wrong over some training data, these models can get really, really good and often even better than the top human annotators, right? Now, if you want to meaningfully use these models for doing science, this is not enough, right? You also need to have some way of explaining what is the scientific phenomenon that led you from this input to this output. And this is where, as artificial intelligence researchers, we get a bit stumped, right? Because very often, once you've trained the network, it's just a collection of a bunch of real number of parameters, and we don't really know a lot about what's going on in there. So you can very often imagine these models as sort of black boxes, and thinking about the state of the art of model explainability, you wouldn't really be wrong at this particular point in time. However, what I want to show to you in this talk is that even though the model itself, once trained, isn't particularly well calibrated, it is still the case that we can use these models to make meaningful scientific and industrial advances. And I'm going to try to make this clear to you in the following few slides. Specifically, we're going to be making a few interventions to this model. The first simple intervention we can ask a model is once this model has predicted something, say cat, because these classifiers are usually probabilistic, we can ask the model how confident is it in this decision. So it might not just give us that this collection of pixels is a cat, it might also tell us that it thinks this collection of pixels is a cat with 97% confidence, right? So these kinds of simple interventions can at least give us some idea on how well does the network rate each one of the possible outputs, right? Another thing that we might want to ask is also, much like our discussion at the beginning, what were the parts of this input that have led to this particular outcome, right? And specifically in this particular case, because these neural networks are built to be differentiable functions, and therefore you can compute gradients of every single part with respect to any other part, you can ask it which parts of this input have caused the highest gradient with respect to the output, and therefore what does the model think are the patterns that influenced it to make this decision. And if a model has been well trained to recognize cats, it may well highlight in this image the eyes and the ears, as we discussed before. Now, here I need to make a very important disclaimer. These methods, especially gradient-based saliency methods, are well known to be super brittle, super liable to adversarial attacks of all kinds, and they're not necessarily giving you any kind of causation, and sometimes not even correlation. So basically, there's a lot of things that could go very wrong with these methods. I like to say they're still in their diapers, and we probably have a long way to go before we can reliably extract what was the input part that was most important for predicting the output. But I do hope to show you in this talk that even at such a rudimentary level, we can already do quite useful and I would say even quite exciting stuff with it. So keep in mind, these two are the main interventions with which we're going to interrogate a neural network. How confident is it in a particular decision, and which patterns in the input caused it to make that decision? Now, in order to show you how these methods have been applied in what we have done, I'm going to actually take a step back and talk to you about my main area of research. I currently do research in the area of graph representation learning, which basically means I am constructing neural networks that operate over graph structured data. Graphs are interconnected structures of nodes and edges. And there's a good reason why I'm very excited about graph representation learning. It is because basically graphs are pretty much all around us, right? You can find them at virtually all levels of organization of life, starting from the basic building blocks, the organic molecules, which, as you can see here, are very nicely represented as a graph of atoms connected together by chemical bonds, all the way to the highest levels of organization of organisms, such as the connectomic structure in the human brain, which you can see in the lower left, very nicely represented as a graph of neurons connected together by synaptic connections. But beyond just being able to explain many levels of organization of life, graphs are also omnipresent in synthetic constructions or human-made constructions, such as transportation networks. You can see in the top right the somewhat outdated rendition of the London tube map, where you can very nicely imagine different nodes as corresponding to different metro intersections and different edges as tube links connecting them. And also, perhaps the most obvious industrially applicable graph structure, the social network, can be very naturally represented as a graph where nodes are users and edges are their friendship connections. Here in the bottom right, you see a somewhat old snapshot of the Facebook friendship graph showing how human interaction often transcends continental boundaries. So they seem to be a very, very natural language for describing basically anything natural or synthetic, and therefore they're bound to be very, very useful to anyone who wants to do any kind of science or industrial work or even general intelligence in the coming years. And of course, I probably wouldn't be standing in front of you virtually here if I did not have some kind of claim to fame, right? If I did not have some way of saying there's something meaningful I have done in this space. Well, for me, this claim to fame is Google Maps. So I was part of a team of researchers at DeepMind that deployed these graph neural network models directly inside Google Maps. We already discussed in the previous slide that transportation networks can be very nicely reasoned about as graphs. And one very convenient feature that Google Maps gives you if you use it is this travel time estimate, this 44 minutes estimate on this particular slide, which tells you for a particular route that you're interested in, how long is it expected that you will travel along this route. This is a very important prediction problem, not only for day-to-day users of Google Maps, but also for the many companies and enterprises that depend on the Google Maps API to predict travel times for their customers. For example, if you're ordering a cab, any kind of ride sharing, food delivery, all of these services rely on predictions from the Google Maps system in order to serve to their customers how much time they will wait before their car arrives, right? So very important problem, which touches billions of people on a daily basis. And as we said, we tried to deploy these graph neural networks so that our time predictor depends directly on the graph structure of the road network. And in doing so, we have been able to significantly improve on the previous baseline in production that Google was using. In fact, on the bottom right, you can see when we initially launched this product, we launched it in a bunch of cities around the world. And in some of them, such as Sydney, the relative improvement compared to the previous Google baseline was over 40%. So we really improved those nasty edge cases where the previous baseline that wasn't very minded about the structure of the graph was not being able to predict travel times accurately. And this also saw quite a bit of attention in the press, as evidenced by this VentureBeat article in the top right. But the key thing I also want to mention here is that this system is now deployed worldwide. So no matter where you are, including Belgrade, if you ask Google Maps for the optimal route from A to B, it is the travel time estimate you're going to get is going to be served by the model that we have developed at DeepMind. Okay. Now, since we said that learning representations over graphs is a potentially useful thing, let me tell you a little bit more about this particular graph structure, which if you're going to start working on graph representation learning, you're very likely to encounter it, and that is the molecule. The reason why it's so easy to get in contact with such data as a graph representation learning researcher is that molecular data is very easy to obtain in large quantities. And as we discussed before, a molecule can be very nicely interpreted as a graph structure of atoms connected together by chemical bonds, as in the case of this molecule here, which is paracetamol, a very important small molecule. So you might be wondering then, if I have a graph neural network and it runs over this molecule, what is something interesting that we could predict based on this molecule? And many of these smaller molecules, such as paracetamol, can be quite important drugs. So most drugs of interest to humans are actually small molecules. And specifically, say, one class of drugs which is quite important in modern life are antibiotics, so molecules that are capable of inhibiting certain bacteria. So we could train a graph neural network to look at a structure of a molecule and predict whether or not it would be a potent antibiotic. In the case of paracetamol, probably not, but you can build a big binary classification data set and train one of these graph neural network models to predict for each molecule, does it inhibit bacteria? Now, one thing which is really cool about this model is that once you've trained it, you can apply it to any molecule, including molecules outside of your training set. So let's then run this molecule over a bunch of, run this GNN model over a bunch of molecules for which we know they are current drug candidates, meaning we might be able to skip some steps of clinical studies because they've already been tested for some unrelated disease. And sometimes it might happen that for molecules where you wouldn't expect it to happen, the model says that they would actually be potent antibiotics. And then you can actually use the first intervention I told you about to ask the model, how confident is it in those decisions? And it just might turn out that for some molecules, like the one you see on this slide, the model not only says it's an antibiotic, but it says it's an antibiotic with like 99% confidence. It seems really, really big, right? Now, I need to stress that a molecule like this was never, ever considered for antibiotics. So for the human expert, it feels very unusual. However, if the model is so confident, maybe it saw something there that the human experts were not able to see. So maybe it's worth investigating. So let's just take maybe some of these molecules that are the highest confident antibiotics in terms of the model and just send them off to chemists. Let's see what happens, right? And it actually happened that this molecule I showed you here, which is called halicin, turned out to be actually a super potent antibiotic. Now, I'm not a chemist, but my understanding is that nobody would really have expected a molecule like this to have antibiotic properties. And that's because it has a very unusual structure for an antibiotic. However, this unusual structure also meant that the mechanism of action of this molecule was very, very different to what you'd expect in most common human-discovered antibiotics. And as a result, it was potent also against bacteria that have over the decades developed resistance to the kinds of antibiotics you put in your system on a regular basis, right? So it was not just any antibiotic, it proved to be really potent. So naturally, the team at MIT that worked on this has published it in a top-tier journal, Cell, and very quickly it got reshared by Nature, by the Financial Times, by the BBC. And you might have actually seen titles like this, Scientists Discovering Powerful Antibiotics Using AI. Well, now you know what that AI is. It's actually a graph neural network, a standard off-the-shelf graph neural network trained to predict whether or not the molecule has antibiotic properties, and then interrogating that model for what are the most confident molecules from a given data set. This is, in my opinion, still one of the coolest examples of graph neural networks applied in synergy with human experts. However, the only unfortunate aspect, if you look at the dates on these articles, 21st of February 2020, all of this happened basically right before the COVID pandemic became big. And at that point, nobody really wanted to talk about antibiotics anymore. Everybody wanted to talk about COVID. So basically, in a way, it was a bit detrimental to the fame of this particular method, but I still think it's incredibly cool. So obviously, this is, in my opinion, I think a really cool application, but I've told you about what a team from MIT has done. I haven't told you anything about something that I've worked on in this space. And now we're going to kind of switch gears and talk about that. Specifically, the question I want you to have in the back of your minds is, can we discover new structure in pure mathematics with the use of machine learning? Right. I must stress, when we initially asked this question to mathematicians, the answers we got were reasonably negative because most machine learning systems rely on having a reasonably high but less than 100% accuracy. Whereas in mathematics, you cannot really publish a paper if you do not have a fully descriptive scientific description of what your model does, right? So there was quite a bit of skepticism, but we still pressed on. Why is that? Well, first of all, let's try to think about how a human actually performs mathematics. Specifically, when you really think about it, you might come to realize that the way mathematicians work is not really by blindly applying logic rules to prove theorems, but actually very often to derive a mathematical result, you need some creativity, you need some imaginative leap of faith. And perhaps there's no better example of this than this mathematician on this slide, Srinivasa Ramanujan, who is notorious for making theorems and conjectures materialize basically out of thin air. And, basically stunning everyone by how he managed to derive this, even though he had zero formal mathematical training. Another great example is the work of this mathematician, Johannes Kepler. If you're not familiar with his work, Kepler laid down the laws of planetary motion, which govern how all the planets in the solar system move. How did he arrive at this conclusion? By staring at huge amounts of astronomical data of where planets were at every point in time. And basically, based on this, he was able to discover a rule. And when he first discovered that there was a regularity in how the planets were moving, he's infamously quoted by saying he first believed he was dreaming, right? So I just started talking to you about how a mathematician might conduct themselves. And we've already talked about creativity, imagination, dreams, right? And this sounds like something that we might be able to influence. So we set out to attempt to build an artificial intelligence system that wouldn't replace a mathematician, but rather whenever a mathematician is in need of some intuitive help or something to help them analyze the complicated objects that they're looking at, can give them the right inspiration at the right time. And we believe that this could form a very interesting and very positive feedback loop leading to some very exciting mathematical discoveries. And clearly, because I'm standing in front of you virtually just now, something must have happened for me to be talking to you about this. And indeed, after 2 years of working on this, we have managed to meaningfully influence two very disparate areas of mathematics, knot theory and representation theory. And the significance of these results was high enough that one of the best scientific journals in the world, Nature, has decided to feature our paper on the cover page in December of last year. And it also received quite a bit of media attention, including this article from the New Scientist. But in my opinion, the media coverage and the cover page of Nature are more incidental, like consequential things. What mattered to me a lot more is if you look at the reviews that we got from the anonymous reviewer, mathematician experts whose basically main job is to give us critical suggestions for improving the paper. They immediately, at the first version of this paper, said something that's a bit of a 180-degree turn from that initial skepticism we've seen from mathematicians. They're basically saying this paper marks the beginning of a new phase in the use of computers in mathematical research. And maybe more importantly, they cannot imagine a mathematician not using these methods if they were available to them, because not using them means progressing much more slowly, right? So seeing such a 180-degree turn is, in my opinion, the really critical part of what our work has enabled to do. So now, for the remainder of my talk, I'd like to tell you a little bit more about what we've actually done. So the two areas of mathematics that we've influenced using this method. And specifically, obviously, I'm not a mathematician by training, and I trust many of you aren't either. But I will try to give you just the necessary backdrop to what we're going to be talking about so that you can understand not so much the mathematical result as much as how the mathematicians were able to synergistically play with the machine learning model as they went on the process of mathematical discovery. The first area, as I mentioned, is knot theory. And specifically for this, we need to talk about what knots are. And knots are not that different from the knots you see in the real life. The main difference here is that the knot has to be a closed curve. So it's a curve in 3 dimensions that loops in and of itself. And these objects are super fascinating, have a lot of implications to many different areas of math, and they're just a really important object to study. Now, when you have a knot structure like this, there are 2 different ways of looking at it. You can look at it literally as this 3-dimensional object and therefore study its geometrical properties. Or you can look at the various knot crossings, like it's a curve that crosses itself in various places, and then think of performing some kind of algebra over those crossings. And one thing that's quite fundamental is that basically, until our work, there have been no strong connections verified between the algebraic and geometric view of a knot, and our mathematician collaborators did not really have any idea on where these connections could be, if there are any. So what did we set out to do? We trained the machine learning model, a neural network that looked at a bunch of geometric properties of a knot and tried to predict one particular algebraic property of a knot, the signature. We chose signature specifically because it was an integer quantity, so we could do classification rather than regression. We believed classification might be easier. And this neural network, much to the surprise of our math collaborators, found a reasonably strong relationship and had reasonably high accuracy. Sometimes the very fact that there is high accuracy can be quite inspirational to the mathematician, that they should pursue this further. But in order to publish a math paper, you cannot just say, I have a neural network and it achieves high accuracy on this data set that I built. We need to somehow figure out what is the actual mechanism with which one of these properties can be predictable from the other. And there, the interrogation I talked to you about before can be quite in handy. So we asked which of these geometric quantities from a gradient perspective were most important for this decision. And you end up with a plot that looks something like this. So for every single geometric variable, we can plot how much, from a gradient perspective, it was important for the prediction of the algebraic property. And it doesn't take an advanced degree in mathematics to see that certain quantities are way more important than others, right? And in fact, that's what we did. We told the mathematicians, hey, you might want to look at the meridional and the longitudinal translation. They seem to be super important. And the mathematicians went away. They studied these two variables for a while, and they came up with a new quantity, the natural slope, which is a simple but nonlinear combination of these variables that suddenly allowed them to find an almost linear relationship to what they wanted to predict. In fact, they were able to make a conjecture that this natural slope is basically 2 times the signature, allowing for a direct connection between the geometry and algebra of a knot. However, to have a full theory, it's not just enough to conjecture. You need to have like an upper bound on how big of an error can be made for this linear estimate. And initially, the mathematicians came up with this upper bound of the square root of the knot's volume, which we could verify on all the examples in our training set. However, if you're really persistent, you can find counterexamples. And in this case, our collaborators found that if you build these knots that are super, super twisted, you can break this upper bound. And this conjecture was actually false. Did this make us give up? Well, not really, because let's go back to this plot on the right. We looked at the 3 most important variables, but if you look at all the other ones, they're far less important, but there is a group of 3 variables that seems more important than the rest: the short geodesic, the injectivity radius, and the cusp volume. So we went back to the mathematicians and we told them, hey, one of these 3 variables might be quite important. Maybe you can use it to fix your upper bound estimate. And indeed, sometime later, the mathematicians were able to take one of these variables, the injectivity radius, and to actually fix their upper bound by using it on the right-hand side. And this was actually a theorem that they were able to prove. So this theorem, for the first time, connects the algebra of a knot, the signature, to the geometry of a knot, the slope, volume, and injectivity radius. And this was actually a quantity that we have been able to prove. And if you look at the cover page of our Nature paper, you can basically see the way it's built is you have this equation that the mathematicians found, which ended up being exactly at the midpoint between the mathematical world on the upper right and the world of the artificial intelligence, which is the printed circuit boards at the bottom right. So now I will tell you a little bit about the second application we worked on. It's one that I worked on more directly. You can see me as one of the authors, which is representation theory. Once again, I won't go into big details on representation theory. I'll just say the main object we study here are permutations. Those are operations that change the order of a bunch of elements in a way that it's still the same collection of elements, just presented to you differently. And specifically in representation theory, what we tried to attack is this long-standing 50-year-old grand challenge problem, the combinatorial invariance conjecture, which tries to find the relationship between a graph of permutations on one side. So this is a graph where the permutations are the nodes, and you draw an edge between 2 permutations if I can do a swap to go from one to the other. And on the right-hand side is a polynomial with integer coefficients. This is a 50-year-old long-standing grand challenge, and there has been really no particular impact on this work in the past 50 years. You might be wondering why that is the case. Well, basically, you need to find a formula that will work no matter what the power of this polynomial. So it must work for q squared, q to the 3, and so on. So you might be wondering, what's the simplest graph where a q squared appears? It actually looks like this. So this here is the simplest graph for which q squared will appear, as noted by our math collaborator in the bottom right. It's one of the easiest non-trivial examples. But already this graph, you don't need to be an advanced degree mathematician to tell that this is actually a really complicated graph to stare at. And it's very hard to find what are the meaningful patterns that happen to derive this particular coefficient of q squared, right? So basically, you can imagine it gets even more complicated when q to the 3 appears, and so on and so forth. So basically, we can even compute these examples using a computer, but once we've generated these graphs, it's really hard to find what is the structure inside them that leads to this polynomial. As you might expect, this is where graph neural networks, my own area of expertise, comes into play. So we trained one of these graph neural networks to predict the coefficients of the polynomial. Based on this particular graph structure. So this graph neural network actually had a reasonably decent accuracy, about 65%, already way better than chance. And this obviously gave our mathematician collaborators very big motivation that there could be something there. But as before, you cannot really publish a math paper based on this. You have to dig into these objects and figure out what's going on. Once again, we tried our basic gradient saliency methods. Since our input is a graph, they will be subgraphs effectively. And I must stress that the subgraphs that our method found were particularly noisy and not very nice to look at. We thought there was nothing there. We thought we would need to publish more stronger methods in explainability. However, we still send them to our math collaborator. Maybe there was something there. And looking at these methods, looking at these subgraphs for a few weeks, our collaborator was able to find that these diamond structures that you have highlighted here in red, they tend to appear quite a bit. So these diamonds might have been quite important. Okay. Now the cycle continues because now we know these diamonds are important. We also know graph neural networks aren't really good at detecting these structures. So we retrained our model with one extra feature saying, is this node in a diamond or not? But otherwise the graph neural network is exactly the same. So our accuracy jumped from 65% to basically 98, 99%. So this essentially immediately gave us a lot of confidence that these diamonds were very important just by a back and forth interaction with the machine learning system. However, we needed one more iteration of interaction with the system to be really confident about what was the important part for the mathematics in this case. And specifically here, because we said, the model will highlight important nodes and important edges, we might be then asking what are the edges that are most important. As we said, basically, every edge in this graph of permutations corresponds to a swap. So say in the 9-element group where we have elements from 0 to 8, we can see which swaps does the model prefer to do. And this heat map, a very simple explanatory data analysis, highlights that the model really likes to swap node 0 with node 8, which basically means the model likes to swap extremal elements. And this turned out to be such a crucial observation, even though it was derived by simple gradient saliency plus exploratory data analysis, such that one of our reviewers basically said the feeling that these extremal reflections seem to be crucial is one they would have expected only from a handful of great world experts in representation theory. And it's such a human suggestion that, I quote, it gave them goosebumps. Okay? So we've been able to have something goosebump inducing from a simple combination of gradient saliency and very basic exploratory data analysis. I cannot begin to imagine what's going to start happening when we actually get good at these methods. Anyway, with the combination of these diamond structures and extremal edges, our math collaborator was able to decompose the graph into these two parts, the inductive part and the so-called hypercube part in blue and green, such that he could prove a theorem that the polynomial that we're after will always be computable as the sum of a part that comes from the inductive part and a part that comes from the hypercube. And there must exist a decomposition that will work in this way. This is actually one thing that our collaborator really likes to stress. The thing that we want, the polynomial on the left-hand side, is computed as a sum of an inductive piece, which is very well understood by experts in the area. So it's a human suggestion. And the hypercube part, which was completely novel to the mathematicians and suggested entirely by the analysis of the AI model that was trained on it. So if I don't know what gives a better estimate of human AI synergy than this. To compute something we care about, we need to sum up a part that comes from the human and the part that comes from the AI. I at least find this to be super inspirational. Now, of course, you might be wondering, does this settle the 50-year-old grand challenge? Well, the answer is no, because we say there must exist a decomposition that works in this way, but we don't tell you how to find it. There could be wrong ones as well. There could be many decompositions. Not all of them could give the correct answer. So we set out to do what any machine learning person sets out to do. We tried to build a database of all of these different decompositions and do like a binary classification. Is it correct or does it give the wrong answer? They all gave the correct answer, which from a machine learning perspective means we have a super biased data set. But jokes aside, from a mathematics perspective, it means that there's a possibility that actually no matter what decomposition you take, you should be able to do this. And if this conjecture is true, it would settle the 50-year-old grand challenge and actually our mathematician collaborator was so confident about the substructures discovered here that they were able to even come up with a proof sketch for someone who's very keen. If you're interested in representation theory and know about perverse sheaves, please go ahead, check out our paper, and maybe you'll find something you can prove there. And before signing off, I would just like to make one last point about what next, right? We have showed that we can use a very simple, basically off-the-shelf machine learning model trained on a well-constructed scientific or mathematical task, and then interact with it in very simple ways, like ask it what's the confidence of a particular prediction, or what are the parts of the input that have the highest gradient with respect to the output. And we were already able to do some very interesting, occasionally goosebump-inducing results in an area that's as pure as mathematics, right? But this kind of idea of trying to infer what's the true generative part of a particular prediction, what are the most important substructures for a particular task, it seems to be a task that's pervasive not just in maths, but across science and across industry. And I need to highlight once again, if we were able to influence the purest science of them all by using a combination of fairly rudimentary explainers and off-the-shelf neural networks, I cannot even begin to imagine what the future has in store when we actually get really good at these methods. And on that note, I'd like to thank you so much for listening. I hope you've enjoyed it, and I look forward to answering your questions, either online during this session right now, or during, in offline communication. You can either reach out to me via email or check out my various social networks on my website. I'd like to once again thank all of my co-authors who have been a great, who have been great in working on this together with me, especially the mathematician collaborators like Andras, Mark, and Jordi. Thank you so much.